Hello grade 9s, this is Mr. Miller, and welcome to lesson 4.4 on similar polygons. So we're going to start off with some definitions and examples, starting with a polygon. So a polygon is a two-dimensional closed figure that's made of 3 or more line segments. The first example we're going to look at is to draw, our instructions are to draw and name the polygons with, starting with 3, that's the minimum number of sides, then 4, and then 5, all the way up to 9, 10, 11, and 12 sides. So here are the first 6, starting with, obviously, a triangle. Now, this particular triangle has all 3 sides equal, and so that makes it a special kind of triangle. We call it an equilateral triangle. With the quadrilateral, if we have all 4 sides equal and all 4 angles equal as well, then this is a square. And with a pentagon, we have 5 equal sides here. We just refer to this as a regular pentagon. So I've put a little star here because a pentagon doesn't necessarily have to have all 5 sides equal, so this is a special one. Same thing with all of the polygons that I did here. I decided to just make regular ones, although I certainly could have made them irregular by making some of the side lengths not equal to each other, or some of the angles a little bit different. Anyway, so here we have a hexagon. It's got 1, 2, 3, 4, 5, 6 sides. Here we have a heptagon. It's got 1, 2, 3, 4, 5, 6, 7 sides. Here we've got an octagon with 1, 2, 3, 4, 5, 6, 7, 8 sides. And now on to the last few. So here we have the next ones, and we have their names as well. And so this one is called a nonagon. Some people prefer to call it an enneagon. And regardless of which of those two you call it, this is a 9-sided polygon. 1, 2, 3, 4, 5, 6, 7, 8, 9 sides. And again, the way that I drew these was to have all 9 sides equal, so I've put a little asterisk here just indicating that it is regular, just like the other ones that I've done here. All of these polygons that I've done, I've decided to make them regular, with all sides equal to each other and all angles equal. So on to the 10-sided polygon. This is called a decagon. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 sides. And now we have another sort of strange polygon. Strange in the sense that not everybody agrees on the naming of this. Some people call it an undecagon, one more than decagon, and some people call it hendecagon. My personal preference is undecagon, but you don't have to call it that. Let's count the sides. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 sides. All of those sides are equal. All the interior angles are equal. That makes it regular. And finally, we have the dodecagon with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 equal sides, 12 interior angles that are all the same. It is a regular decagon. So now a few more definitions and examples. First of all, let's talk about two similar polygons. Similar polygons are the same shape but not necessarily the same size. And here's how you can tell that polygons are similar. So the first clue is that the corresponding angles are equal to each other. So that's only going to be a guarantee that two polygons are similar if you're dealing with triangles. When you have a quadrilateral, I'll just illustrate this, that if you have a quadrilateral, and a really simple example to look at here is with a rectangle. So let's say that you have a rectangle and the sides are maybe of length 2 centimeters and let's say 4 centimeters, and then you've got a square which is 2 centimeters by 2 centimeters. Now, what's interesting to note here is that the corresponding angles are all equal to each other. All of the angles inside here are 90 degrees. These are all right angles. And inside the square, we also have all 90-degree angles. But the thing that you're going to find that's different is that the ratios of the corresponding side lengths are not the same. And that means that they are not similar to each other. So there's a 1-to-1 ratio between the widths here, but the lengths there's a 2-to-1 ratio. And the fact that they're not the same means that they're not really similar to each other by our definition of similarity. So for similarity of polygons, you have to have both of these facts. Not only can do the corresponding angles have to be equal to each other, but as well you have to have the ratios of the corresponding side lengths that are equal to each other. So just because you have the interior angles equal with a quadrilateral or a pentagon, hexagon, heptagon, and so on, it doesn't mean that they're necessarily similar to each other. To really verify it, you have to take a look at the side lengths. So triangles are a little bit different in that way. If you know that the interior angles are all equal, then you know you have two similar triangles. Our next example, example 2, we want to decide if each pair of polygons is similar and explain. So we've got CDEF, CDEF, and RSTU are parallelograms, RSTU. The fact that they're parallelograms means that the opposite sides here are parallel and they're equal to each other. EF and CD are also parallel and equal. And so the same thing goes here for ST and RU. They're parallel and equal to each other. And RS and UT are also parallel and equal to each other. So let's see if we can determine whether these two are similar. I mean, they're definitely the same kind of shape. They're both quadrilaterals and they're both parallelograms, but we're not really given the measure of any angles in here. We could measure the angles, but that's a little bit of trouble. Why don't we just use the given information, which is about the side lengths. So if we compare corresponding side lengths, I'm going to compare the shorter side of this parallelogram with the shorter side of that parallelogram. So doing RS over CD, as we've done here, RS over CD, 2.7 over 1.8, that is a 3-to-2 ratio. So if you were to take this and you wanted to get it as a fraction in lowest terms, you could multiply the top and the bottom by 10, that would give you 27 over 18. You divide the top and the bottom by 9, and that would reduce down to 3 over 2. So now we also need to look at the longer sides which correspond with each other. So we're looking at the longer side length on this parallelogram and comparing it with the longer side length on the other parallelogram. So 5.4 over 3.6 is another ratio that we can put in lowest terms. We multiply it first by 10, top and bottom, you get 54 over 36, and then dividing the top and the bottom by 18 would reduce it to lowest terms. It turns out to be 3 over 2 as well. So we know that these parallelograms are similar to each other because the ratios of the corresponding side lengths are equal to each other. Now we have another two quadrilaterals, and this time they're not parallelograms. So we want to know if these two are similar to each other. And so what we're going to do is we're going to compare XY and NO. The reason XY and NO is because this is the longest side of this quadrilateral and NO is the longest side of that quadrilateral. So if these two quadrilaterals are similar, those would be the corresponding sides. So that ratio, 28.4 over 14.2, is exactly 2. Now if we move on to another pair of sides, so looking at WZ, which is the side opposite to the longest side, MP is the side opposite to the longest side, comparing 26.4 and 12, that ratio is 2.2. And right away we can see that 2.2 and 2 are different. So because of that, we know that these two quadrilaterals are not similar to each other. And that's because the ratios of the side lengths that should correspond are not equal. So one more example. Example 3, the two pentagons here, DFHIJ. DFHIJ. That is one pentagon. The other pentagon is EFGLK, and they are similar to each other. Now, another key thing to know about these similarity statements is that D and E correspond with each other. So the angle at D and the angle at E are equal to each other. The angle at F and the angle at F, well, obviously it's the same angle. The angle at H and the angle at G, so this angle and that angle are equal. The angle at I, as well as the angle at L, are the same measure. And J and K, the angle here at J, the angle here at K, they are the same. Also, if you look at DF, that side length corresponds with EF. Those two sides are corresponding to each other. It just helps you get an idea of how to determine what corresponds to what in these figures. So the instructions here are to determine the missing length x and to show your work for that. So we're given 1, 2, 3, 4, 5 different side lengths. We need to find out what x is. Of course, we know that x corresponds with 6.3 because GL here would correspond with HI. So we need to use another pairing of corresponding sides to figure out that missing side length. So here's what we're going to do. We're going to take a look at DJ and EK. DJ is 6.72 and EK is 3.2, and that ratio should be the same as the ratio of HI over GL. So now putting in all the values that we have, of course the one thing that's missing is GL, that's X. Now we have a proportion that we can solve. My personal preference is just to cross multiply and divide. So I multiply the two numbers that are diagonally across from each other that are known in the proportion, and then divide by the third number in the proportion, which is 6.72, and that will have you arriving at your final answer, which is that X is 3 units. So those are all the examples for this lesson. Thanks for watching and have a great day.